Hello, everybody. This is going to be a quick demo on how to build a parallel program. In this program, we're going to compute the hypotenuse of a right triangle using the Pythagorean theorem, both sequentially and in parallel. So the first thing I'm going to do is I know the name of this class. It's right triangles that I want to find. I'm going to hit Control-Shift-T because this is a Windows machine. Either on Windows or Linux, you can do Control-Shift-T. On the Mac, it's Command-Shift-T, and you get this nice open type dialog. I could type right triangles and sort of narrow it down that way, or I can type try star and star try star, and it'll show me all the ones that have that in it. And I can just click on right triangles. Now, if I run this program, it throws a not yet implemented exception right away. We're trying to print out the hypotenuse of 3 and 4 for A and B. Quick spoiler alert, that's 5. This is the 3, 4, 5 triangle. And we can see here, I can click on the lines in the stack trace and sort of show the bottom of it, or here's where we first call it. When I come up here, there's my not yet implemented exception, which you will encounter a bunch in this class. And what we want to do is we want to build this. And so I can delete that line. I just hit Control-D, Command-D on Linux. I can fire up my favorite search engine and just type in Pythagorean theorem. Nicely, Google now has this thing that just shows you C is the square root of A squared plus B squared. I can test this out with 3 and 4. And it shows me that's 5. I can go right here to the Wikipedia page where I can see a even sort of interesting description of this. Here's the A squared plus B squared equals C squared. Hopefully a lot of you remember this. I'm going to copy this URL and come back to Eclipse. And the first thing I'm going to do is just paste that in there so that anybody, first of all, give a shout out and appropriate amounts of credit to both Pythagoras and Wikipedia, but also anybody who comes along and tries to figure out what I was doing here can sort of see what algorithm I'm using. So I'm going to say A squared. I make a new variable, A squared equals A times A. I'm going to make another variable, B squared equals B times B. And so then compute C, which is, of course, as we found out from our Google search, C is the square root, called the math function, sign, square root, A squared plus B squared. I hit Control-Shift-F there, which formatted everything. If you have like crazy indentation and, everything's off, if you Command-Shift-F, it'll sort of space everybody out. If you have, bad spacing, Command-Shift-F or Control-Shift-F is your friend. So now when I run this program, you can see it produces 5 correctly, and that's nice. This is a sequential program. And so if we look at what's called a computation graph, it's very straightforward. This is sort of how all of your sequential programs you've ever written look like. There's just a bunch of statements that are executed one after the other. In this case, we are computing A times A, and that happens first. And then we move on to do B times B, and then we take the results of those two things and pass them into square root, and that is our program. And when we want to write a parallel program, what we're going to try to do is we're noticing that the first thing hopefully you're noticing is that these two statements, the calculation of A squared and B squared, are completely independent of each other. And so we can run those two in parallel. Now, we need them both to complete before we pass it into square root, right? And so we're going to use 2 constructs, fork and join. You can imagine sort of creating a fork in the road. We're going to do this calculation and this calculation in parallel, and then we're going to join those 2 lines up in the end. Now, instead of just calculating this A2 directly, I'm going to make some A to A squared future, and I'm going to call fork. Now, fork needs us to be able to specify what we wanted that computation to be. And in this case, what I'm going to do is just return A times A. Now, I need A2's value, this future, which can run in parallel before I can call square root. So I can get that value by calling join on the A2 future. Run this program again. I hit Control F11 on its command on the Mac, and that still computes 5. So we still have a correct program, but now this code right here and this code right here can run in parallel. This join makes sure that A2 has completed, this work up here is, this task is completed before we call square root. And if you look at what the computation graph looks like for this, you can see we have the fork call, which will create one of these spawn edges right here so that the A times A work can be done in parallel with the B times B work. Join makes it so that there's this join edge that comes together with the continuation, this sort of normal sequential program, right, before we move on to square root. And so we will write a lot more interesting parallel programs in this class than this. This is just the first one, including ones where there's enough work in these two statements that justifies the amount of overhead or cost of creating a parallel program. As a quick spoiler alert, this is not enough work. Just doing one multiplication is not enough work to justify doing this fork and join, but it's still a perfectly valid parallel program. These two statements can happen in parallel. We need to join them together before we move on. And there you go. That's the first parallel program. And hopefully you'll enjoy writing even more interesting ones in this class.